Hi everyone, this is Mrs. Jackson. This is Chapter 2, Section 4, Part 1, and in this video we're going to take a brief break from quadratics to talk about a brand new concept called imaginary and complex numbers. In the last section, we looked at factoring and how to solve for the x-intercepts of a quadratic function. And if we just had some kind of quadratic here, I'm writing a standard form generalized, and we replaced that y with 0, we will be right on that x-axis, because all along that x-axis y equals 0. And through factoring or other techniques, which we'll learn later in this chapter, we are solving for the x-intercepts. Well, some functions will never cross the x-axis. For example, we could have a function over here. It's downward facing. It's never going to approach that x-axis, and therefore we will not have real solutions. This x-axis is a real number line. However, it does have a certain type of solution, and we call those solutions imaginary and complex numbers. And when I first introduce this concept, I tell students, think about an imaginary friend. So a little person, a young person, may or may not have an imaginary friend. This friend isn't real, but it's somebody that this young person talks to. It's kind of like that. So these solutions are not real. They will not touch a real number line, and we call them imaginary. Now, last year I had a student who said, well, who makes this stuff up? And the fact of the matter is it's been around a long time. So the first reference we have in history was from an Italian mathematician. His name is Girolamo Cardano. And that was in 1545. Okay, so been a long time that we've been talking about imaginary numbers. Girolamo was struggling with how to describe solutions to cubic equations. In other words, an equation that has a power of 3 in it. I'll just write something here. We're actually going to be doing that in the next chapter. So he was grappling with that. You can actually take a cube root of a negative number, and that's where he was struggling with that and trying to come up with some concepts around that. Later on, the word imaginary was given by a very famous mathematician, René Descartes. And he's French. He developed all kinds of math that we continue to use today. In 1637, he talked about these types of solutions to these cubic equations as being imaginary, and that name stuck. So since 1637, humans have been calling these types of solutions imaginary ever since. But just fun fact here, Descartes, if you've ever heard of the Cartesian coordinate plane, the XY coordinate plane that we use it has been for years called the Cartesian coordinate plane, and that was developed by René. Okay, so what are imaginary numbers? So imaginary numbers, certainly, as I've said, you can realize it's an abstract concept. So they're not real numbers, and so far in your life, you've only ever discussed real numbers. So this is the first time you're looking at anything that's not a real number. Imaginary numbers cannot be graphed on a real number line because they are not real numbers. So that's one thing to note right away. And the x-axis is a real number line. So the imaginary unit, we use a lowercase cursive I for imaginary. And that unit is equal to the square root of -1. As you know, up until now, you've been taught that you cannot take the square root of a negative number. And that's certainly true. However, there are real applications where we want to, and we model quite a lot of applications with this concept. And so we have basically defined this imaginary unit as the square root of -1. Now, if I actually took this equation here and I squared both sides, so I'm going to do that in color. If I squared this side, whatever I do on one side of an equal sign, I have to do on the other for equality. And if I do that, then I squared equals -1. And so this concept here is really important. So imaginary unit is the square root of -1. It is not a real number. However, if I square that imaginary unit, I do get a real number out. I get the number -1. Okay, let's look at some simple examples then of imaginary numbers. So if I take the square root of -16, up until now you've said that doesn't exist. And certainly a real number doesn't exist out of that. However, we can look at -16 as 16 times a -1. If I take the square root of 16, I get two answers out. I get the positive and the negative version. So I get positive and -4. If I take the square root of -1, I get an imaginary unit. So it's positive and -4i. Another example, I'll try another perfect square. The square root of -81. That's the same thing as 81 times -1. The square root of 81 is both the positive and -9. And the square root of -1 is I. Let's do one more example, say, of something that's not a perfect square. If I have the square root of -8, for example, I can look at that as +4 times 2 times a -1. And I'm going to take my perfect square out, which is +4. And I get the positive and -2. The square root of 2 cannot be done here because it's not a perfect square, so that remains underneath the radical. And the square root of -1 is I. Okay, so let's take a look at this in a generalized form. We generalize an imaginary number using a coefficient b just as a placeholder, I, where b is any number, any coefficient. It could be irrational or rational. And I equals the square root, the square root of -1. Okay, so on the next page, let's take a look at how this concept of an imaginary number relates to our number system that we're familiar with. Okay, so first let me introduce to you a new term called a complex number. So a complex number is generalized as follows: A plus BI. A is any real number. So it's any number that you have been familiar with up to date here. So A is a real number. And the BI, as we just said on the previous page, is imaginary. It's an imaginary piece. So a complex number, and complex in this context doesn't mean complex meaning complicated. Complex, think about an apartment complex where you're bringing multiple units together. That's really the context that we're using this word. A complex number is made up of a real piece and an imaginary piece. So how does that fit into what we already know? Well, what we know and what we're familiar with so far is the real number system. And technically, that real number system is considered a subset of complex numbers. So if we kind of look at this pictorially, it may not look like it, but this is a Venn diagram. So as you know, a Venn diagram is a way that we kind of compare and contrast. And in math, we use Venn diagrams to show sets subsets, and supersets. So I'm going to start here by introducing this concept with this blue bubble here. And I'm going to call that what we know so far, which is the real number system. So I'm going to say, let's call this the real number system. And that's what we're mostly familiar with. Instead of going kind of top down, let's start bottom up. So I'm going to go into the smallest subset here in the real number system. And that smallest subset somewhere in space and time you learned about are called natural numbers. I'm going to abbreviate here. Natural numbers are if you were counting things and you started out like counting marbles. You would not start out with 0, 1, 2. You would start out with the number 1. So the natural numbers are just the natural counting numbers. 1, 2, 3, ... And the next set above the natural numbers is when we would add the number 0. And we call those whole numbers. So whole numbers is the natural numbers, including 0. So we would start out with the zeros. And then if we take a step further and we go up the ladder into a bigger set, we would call those the integers. And integers are the positive and negative counting numbers, and also include 0. So I'll start out here, maybe I'll ... -3, -2, -1, 0, 1, 2, 3, ... So those are our integers. And then the next superset up above the integers are what we would call the rational numbers. So the rational numbers include integers, the rational numbers include wholes, the rational numbers include naturals, but the rational numbers also include things like fractions or decimals, 1/3 or 6/10. And if you're not a rational number, then you're an irrational number. So irrational numbers are over here on the side in the real number system. Irrational numbers are numbers, technically the textbook definition is that it's a number that cannot be written as a fraction of integers. So an irrational number would be numbers like pi, or the square root of any imperfect square. So say the square root of 2, the square root of 5. If it's not a perfect square, that's going to be an irrational number and cannot be written as a fraction of integers. And when we combine these irrational numbers with irrational numbers, we get our real number system. So this is the universe of numbers that you've been knowledgeable on so far. However, we now have this imaginary piece. So we've got imaginary numbers over here. They are not real numbers. And as we already talked about, imaginary numbers are generalized as BI. And the entire piece, the real and the imaginary, come together and we call them complex numbers. So the complex number system is the ultimate superset, and it is referenced or generalized as A plus BI, as we just said. And so over here in the real number system, B equals 0. There is no imaginary piece. And over here in the imaginary system, A equals 0. There is no real piece. So these two building blocks, if you will, come together to create complex number system. So in this video, I introduced the imaginary unit, I, and we put that together with a real number, and we call that a complex number. Hope this video helps. Thanks for listening.